this, if I ask you what makes soda pop, why is a pop a pop? You know, how can you answer that question? What makes Coke, a bottle of Coke, a bottle of Coke? It sounds stupid, doesn't it? It's like, what a stupid question. Well, answer it then. If you're so smart, answer it. You know, I mean, you can't. I can't, right? But we try the best that we can to come up with logical explanations for things, okay? And another thing that you should hopefully understand, that I'm in a position, I think, where I can try to articulate that to you, is just because you understand the mechanisms of something, just because we can talk about carbon dioxide and water and sugar, doesn't mean that we've explained away the origin of something or that we've explained away the purpose of something. We just have a better understanding of that which is in front of us. That's all. Okay? So don't try to think that I'm trying to go one way or the other on that. But it's just important to keep in mind. Okay, so let's just take the three main chemical ingredients of pop. We've got water, sugar, and carbon dioxide. Okay? We know water is H2O, right? Sugar is going to be a bigger molecule, okay, C11H22O11. That's going to be sucrose. Actually, in this case, fructose. High fructose corn syrup, right? Good stuff. Carbon dioxide. So if I ask you what makes pop, give me some characteristics, some properties, just so we know what properties mean. Give me some properties of soda pop. What can you say about it? What do I mean by that? See if you can glean that meaning that I'm looking for. Anything. Okay, it's fizzy. What else? It's liquid. Okay, 2 for 2. Perfect. What else? Okay, sort of a caramely color. It's got caramel additives added to it. Okay. What else? What about the taste? What does it taste like? Sort of a sweet taste, right? Let's stick with those three. We said fizziness, it's a liquid, and it's sweet. Why? Why is it those three things? You can actually attribute those three characteristics to three specific chemicals that are in pop. Okay? For example, why is it liquid? Because it's got H2O molecules in it, right? Water. Why is it sweet? Because it's got sugar in it. Why is it fizzy? Because it's got carbon dioxide in it. Why is it fizzier on a warm day as opposed to a cold day? We'll learn about that later. Okay? So that's where I'm going with that. Now, I want you to know that it's all about, it's like shuffling a deck of cards, right? You've only got so many cards. We've only got so many elements to play with, different types of elements. We can stack them in all kinds of different ways to make all kinds of different things. Okay? Atom versus element. Who can tell me the difference? What's the difference between an atom and an element? It's a simple difference. It doesn't require much thought. That's right. Atom is the simpler of the two, meaning that atoms make up molecules, right? So here we've got 3 atoms that make up one molecule. This is carbon dioxide, a carbon atom, 2 oxygen atoms. We've got a water molecule made of 2 different types of atoms, 3 atoms total. We've got hydrogens and an oxygen. Notice that in both of these cases, oxygen is present, right? Does that mean that these two act anything the same? No. Just because they both have oxygen present, it has to do with, okay, what else is there besides oxygen? How many oxygens are present? Not only that, but look how this is a straight line and this one's bent, right? Why is this bent? We'll learn that in like chapter 10. We'll talk about that a little bit later. But the fact that it is bent means it's going to act different than what this does. This is a liquid, right? At room temperature. This is a gas. This is relatively unreactive. This is a really good solvent to clean stuff with. Why? What's all the difference? You know, we're going to talk about that a little bit later. So we're just setting ourselves up right now. Okay, I already did all this. Talked about what chemistry is and looking for atoms and molecules. Okay, here's where we get started here. Now, at first, you know, I told you that, did I not hand out the, why didn't you guys tell me? Here I am talking about all this. It's a good thing we're just starting. I got all your notes here. So here everybody's jotting down all these notes. I'm thinking, why? Why don't you just write on your paper? Because you don't have it. You guys got to speak up. Well, we haven't covered anything major so far. Only a couple slides here. So. But anyways, I told you that everything is going to build. Everybody sign the attendance sheet? Oh, okay. Everything is going to build And I know that right now what we're getting ready to talk about is not atoms and molecules, but it is something that goes into the calculations involving atoms and molecules, so we got to know this. The next one I'm handing out, it says Chapter 3, but actually within it is also Chapter 4. So you have everything you need for the first test with these notes here. Chemistry is a lab-based science, so it is very important that we know how to interpret numbers and that we measure things properly, and that's what this beginning part is. It's about numbers that we're going to use in our calculations and how things differ a little bit from traditional math. Okay, so what is a measurement? Sounds boring, but I want to make sure that you understand the difference. Okay? When I say the word quantitative observation, what do I mean by quantitative? I mean numbers. I mean you can assign a number to it. For example, if you light something on fire and the flame that is burning is red, and you say that is a red flame, that's a qualitative observation. Qualitative. If, however, you say that flame is emitting at a wavelength of 690 nanometers. That's a specific color, according to a measurement spectrum, that is measurable, involving numbers. That's a quantitative observation. Okay? Quantitative observations are very, very important, okay, in the hard sciences, in chemistry, biology, that kind of stuff, because that's where your data comes in. That's where your proof, that's where your evidence is of what you're trying to claim. It's also a comparison to agreed upon standard. What I mean by that is, we have a U.S. Department of Weights and Measures for our country, right? That says what an ounce is, what a pound is, what a gallon is equal to. These are agreed upon standards, okay, that we have to reference. We can't just say make up our own. If no one knows it, then what's the point? We have to have something that's agreed upon. This is very important. Make sure you take this to heart. You give me a number in this class, you better have a unit for it. Otherwise, it means nothing to me. Thus, I will not grade it, okay? If you say 1 watt, 1 year, 1 second, 1 kilometer, 1 centimeter, too ambiguous. I got to know the unit. Okay? Okay, not to get on a soapbox or anything, but let's take a look at, I don't know, global warming. Probably gone up since these slides were made, but let's say that the global temperature has risen on about 0.6 degrees Celsius over the last year. What does that mean? Well, I want to look at a couple things about this measurement. Number one, notice that I have a 0 point and then one number. Not two numbers, not three numbers. I don't have 0.600, I have 0.6. How do you think 0.6 compares to 0.600? Which one's more precise, do you think? Which one reflects greater, greater certainty in your measurement? Yeah, the more zeros you slap on the end of it, the more certain you are saying that, hey, this is how exact I know this measurement is. The faster you cut it off over here, the less certainty you are expressing in the data that you are giving. So, in math, when you're doing number calculations, yeah, 0.6, 0.600 all gives you the same value, right, when you're doing math. Chemistry, it's not going to, because we're going to have to incorporate something called significant figures here in a minute, okay? All right, so that number, the degree Celsius, tells us that's the standard. So 0.6 means it's risen 0.6 of a degree of Celsius, which is what our standard is. Okay, that's easy, you know that. But what does this mean? Well, look, all that we can say for certain is that this measurement is somewhere between 0.5 and 0.7. We don't know where they rounded. If it was 0.55, they could have rounded up to 0.6. If it was 0.64, they could have rounded down to 0.6. We don't know. So notice the big window of uncertainty that we have here. Versus if that said 0.600, look how much narrower this window becomes in terms of our uncertainty. That's very important in measurement in the lab. Okay? We want to get as certain as we possibly can to add credibility to what we are claiming.